Yes, at resonant frequency the electric and magnetic energies are equal and they are in quadrature, and also when the electric energy is maximum the magnetic energy is 0, or if the magnetic energy is maximum the electric energy will be 0. So generally at the resonant frequency, that is if we consider the any band pass filter response or like that, so resonant frequency means like this you will be getting, and so at this resonant frequency generally we call it as the resonant frequency f0, and at this frequency the electric charge and the magnetic charge are always equal, the electric and magnetic energies are always equal, and also they are in quadrature. Right, anyhow, so the total energy stored in a resonator can be obtained by integrating the energy density over the volume of the resonator. So generally here we are taking a rectangular cavity resonator or a circular cavity resonator. So it is having some volume, and if we integrate the energy density over this volume we are going to get what is the energy stored, and once we get the energy stored we can integrate the energy loss over a area, surface area for obtaining the power loss in the cavity resonator, so that once we get this energy stored and the power loss we can find the quality factor. Anyhow, so first let us define this for the total energy stored, that means we are going to derive for the W. So to get this W we need to integrate the energy over the volume of the cavity resonator. For example, if you take the rectangular cavity resonator, it is having the dimensions. Suppose if you take the rectangular cavity resonator, it have the dimensions A, B and D. So if we integrate the energy density over all these dimensions, over the volume of this, that means this entire we call it as the volume. So over this volume if we integrate, then we are going to get the energy stored in the resonator. Either we can integrate the electrical charge or the magnetic charge. Right. So how we are going to define the electrical charge or the magnetic charge? So the energy stored due to the electrical charge, we define it as integral epsilon by 2 magnitude of E square over the integrate over a volume. So if suppose if it is a rectangular waveguide, then we get it as integral 0 to A, integral 0 to B, integral 0 to D, like that. All the dimensions we consider, and we integrate E square over the intervals. So if it is a magnetic charge, then the magnetic charge is also defined as Wm in terms of the magnetic field intensity magnitude square, H square. And here where in this definition, that means we are saying that the electrical charge stored and the magnetic charge stored at resonant frequency is always the same, and let us consider it as the total energy stored. So here in this We is representing the electrical energy and Wm is representing the magnetic energy, and magnitude H and E are representing the peak values of magnetic and electrical field intensities. Okay, so this is the peak value of the magnetic field intensity and this is the peak value of electric field intensity. So by integrating the electric field intensity over the volume, we are going to get electrical energy stored. By integrating the magnetic field intensity over the volume, we get the magnetic energy stored due to the magnetic field intensity. Anyhow, in the cavity resonator, at resonant, the electric field energy and the magnetic field energy are same, the stored electric field energy and magnetic field energy, and so that is equal to W. So the average power loss in the resonator can be evaluated by integrating the power density over the surface area, So here first energy stored is obtained over the volume, energy stored is obtained by integrating over the volume, and the power loss is obtained by integrating over the surface area. Okay, so by using this definition we can obtain the power loss, and anyhow generally that is defined as 1 by 2 integral Rs magnitude of H square. Suppose if you consider the magnetic field intensity, we can get the power loss in the resonator due to the magnetic field intensity is given by 1 by 2 integral Rs magnitude H square. Here that means the power loss generally is represented as P. P is equal to 1 by 2 integral Rs magnitude of Ht square over the surface area, whereas energy stored is obtained as the integration over the volume, and here the power loss is obtained as the integration over the surface area. And here Ht is the peak value of the tangential magnetic field intensity, and Rs is the surface resistance of the cavity resonator. Okay, and generally this Ht is the peak value of the tangential magnetic field intensity is always twice that of the H square magnetic H square. And if we substitute that 2 and 3, that means energy stored and the power loss in the Q factor definition, because we know that the Q factor Q is equal to omega W by P, where W is the energy stored and P is the power loss. So equation 3 represents the power loss and equation 2 represents the energy stored. So if we substitute these two, we can obtain the quality factor. So Q can be defined as now omega instead of W integral mu by 2 magnitude of H square dV over the volume, and P is 1 by 2 integral Rs magnitude of Ht square dA. Okay, so this 1 by 2 in the numerator and denominator get cancelled, and mu can be out of the integration, omega mu integral magnitude H square over a volume and Rs integral magnitude Ht square dA. Okay, so now since the peak value of the magnetic intensity is related to the tangential and its normal components, so the total magnetic field intensity magnitude of H square can be taken as the sum of the peak value of the tangential magnetic field and the normal magnetic field components. So there is a relation between Ht and H, where H square is equal to Ht square plus Hn square normal. Okay, so also where Hn is the peak value of the normal magnetic field intensity and Ht is the tangential peak value of the tangential magnetic field intensity, we have a relation between Ht and H, that if we consider this Ht is the tangential magnetic field, always this is approximately equal to the twice that of the magnetic field intensity averaged over the volume. Okay, so that means we can consider this Ht square is nothing but equal to 2 magnitude square, 2 magnitude H square. Okay, so the Q of the cavity resonator can be defined as Q is equal to omega mu. If you integrate it over a volume, we are simply considering it as a volume, and as Ht square is twice that of the H square, we are taking it as 2 Rs into surface area, because this is integral over a area and this is integral over a volume. So let us consider integral of volume is resulting volume and integral of surface area is resulting the surface area. So where here we get integral Ht square, but Ht square is nothing but 2 H square, so we get it as omega mu into volume by 2 Rs into surface area. An unloaded cavity resonator can be represented by either a series or a parallel resonator circuit, series LC circuit or a parallel LC circuit generally. So we can also find the unloaded quality factor of the resonator. So that can be represented as unloaded quality factor can be represented as Q naught quality factor, and resonant frequency can be represented as F naught Okay, so those can be defined, that resonant frequency and quality factor of the unloaded cavity resonator can be represented as f naught and q naught, and f naught is given by simply 1 by 2 pi root LC is a well known definition from previous years itself. We have seen for even a band pass filter we get f naught is equal to 1 by 2 pi root LC, and from this we can also obtain the quality factor q naught, where q naught is equal to L omega naught by R or omega naught R by C. We have different relations depending on the inductor or capacitor circuit. Okay, anyhow the unloaded quality factor q naught here is represented as L omega naught by R, and unloaded cavity resonator frequency f naught is equal to 1 by 2 pi root LC. Now let us see how we can derive the quality factor of a different cavity resonators, like a rectangular cavity and a circular cavity resonator. So first let us see the Q factor of a rectangular cavity resonator. For this let us see what is the mode that is propagating through this rectangular cavity resonator, and let us consider it is a TE mode. So as it is a TE mode, Ez is equal to 0, and we know that the Hz is equal to C sin P pi by dz cos m pi by a x cos n pi by by e power j omega t. We are considering it is a TE. As it is a TE, Ez is equal to 0. Okay, let us consider a rectangular cavity resonator and the propagating mode is a TE mode. So Ez is equal to 0, and Hz is C sin P pi by dz cos m pi by a x cos n pi by e power j omega t. Now if you find the field components of this Ez of this Hz, so that means if we define the field components, so generally the field components means we have Ex, Ey, Ez, Hx, Hy, Hz. Anyhow Ez and Hz are there already, so the remaining field components are Ex, Ey, Hx, Hy, and if we find all the field components except Ex, all other field components will get vanish for this. If we substitute if we derive this, okay, and substitute the cos and m, n, p values, then all the field components get vanish except Ex. Okay, so let us find what is Ex. Ex is equal to minus j omega mu by h square dou Hz by dou y. So if you differentiate this Hz with respect to y, then we are going to get what is Ex. So if you differentiate this with respect to y, that means except this y component, all the other components becomes constant. So you are going to get Ex is equal to minus j omega mu by h square, and all these are constants except this cos n pi by b y becomes minus sin n pi by b y into n pi by b e power j omega t. So let us see what is Ex. So we get all the remaining terms as it is, C sin P pi by dz cos m pi by a x, and the differentiation of this cos n pi by b y is minus sin n pi by b y into n pi by b into n pi by b will be having, and that is taken it as a constant C. Anyhow we can take it as a n pi by b sin minus sin n pi by b by e power j omega t. And so now we are going to get, if as we are considering that T011 mode, okay, and as it is a cavity resonator, rectangular cavity resonator, so in rectangular cavity resonator we have the dimensions m and p as it is, but if it is a circular cavity resonator, generally the notation will be nmp. Okay, anyhow as it is a rectangular cavity resonator, m n p we are taking, where m is 0, n is 1 and p is 1. So that p term will remain as it is, sin p pi by d, p is 1 and m is 0. Okay, so here we take the entire this constant minus j omega mu by h square c n pi by b, we can take it as a peak value and we take it as a e naught sin p pi by dz and sin pi by b, that means n is equal to 1 So it becomes sin pi by b y e power j omega t, and as m is 0, cos 0 is 1, so simply we ignore this term, and so we get this equation 10. Ex is equal to some E naught sin pi by d z sin pi by b y e power j omega t, where E naught is the peak value. That means especially here, what is E naught is this minus and minus will get cancelled, and so we can simply say where E naught is nothing but equal to simply j omega mu by h square n pi by b into c. This we can consider it as a peak value E naught. Okay. So once when we get that E naught value and Ex, we substitute that in the energy stored. Anyhow, as we have defined the energy stored is represented as a W. Here we have taken it as E stored, or we can call it as a W. So this W is equal to 1 by 2 integral over a volume. So integral over a volume can be taken it as integral 0 to a, 0 to b, 0 to d, e square dx dy dz. Anyhow, actually this e square can be taken as ex square plus ey square, but only ex is defined, so simply e square can be written it as only ex square, because since the electric field, total electric field intensity, we generally write it as magnitude of ex square plus ey square, and here as this field components get vanish, we take magnitude e square is equal to ex square and we substitute that here. So as we substitute that here, we get the energy stored is equal to 1 by 2 integral 0 to a, 0 to b, 0 to d, E naught square and sin square pi by dz, sin square pi by by dx dy dz. Anyhow, here E naught square is a constant, so it comes out of the integration, and so we can write it as E naught square by 2 integral all, and sin square function is there. So we know the trigonometric relation that sin square x can be written as 1 minus cos 2x by 2. So we can substitute this relation, and so we can find that the energy stored can be represented as equal to, okay, here 1 by 2, or we write it as E naught square by 2 integral 0 to a integral 0 to b, 0 to d, and this sine function we can write it as 1 minus cos 2 pi by d z by 2 into 1 minus cos 2 pi by b y by 2 dx dy dz. So these denominator 2's we can take it out of this integral, and simply this energy stored we can write it as E naught square by 2 cube, okay, E naught square by 8, and here it is a function of z and it is a function of y. Anyhow, let us take integral 0 to a, okay, integral 0 to b 1 minus cos 2 pi by b y integral 0 to d, you can take it as a dy, here dy integral 0 to d 1 minus cos 2 pi by d z into dz dx. Okay, so now that means we can take this dy also here we can take dy dx. Okay, so now we get the energy stored is stored, or the energy stored is equal to E naught square by 8 integral 0 to a integral 0 to b 1 minus cos 2 pi by b y integral 0 to d 1 minus cos 2 pi by d. That integration we can resolve, and we can say integral 1 is always results integral 1 dz, we can write it as z minus integral cos is sine 2 pi by d z by 2 pi by d over the limits 0 to d dy into dx. And when we substitute this d here in this upper limit, this sine function becomes sine 2 pi, it becomes 0, and if you substitute the lower limit also, it becomes a sine 0, that is also 0. So this term will vanish whether it is for d or 0, and so we get, if we substitute d in place of z and 0 here, d minus 0, so this entire value is resulting some d, so we can get energy stored is equal to E naught square by 8 integral 0 to a integral 0 to b 1 minus cos 2 pi by b y into, and this in the place of this z we get d minus 0 dy into dx. So this is E naught square by 8 integral 0 to a, simply here d is constant, so it can be out of the integral, so we can write d outside the integral, and 1 minus cos 2 pi by b by dy. So the integration of this is going to result y minus the integral cos, we get sine 2 pi by b y by 2 pi by b over the limits 0 to b dx. So that means now if you substitute y is equal to b, here it becomes sine 2 pi becomes 0. If you substitute y is equal to 0, also this function becomes sine 0, that is 0. So this sine function will vanish for both upper and lower limits, and so we substitute in place of y what is these upper and lower limits. So in place of y, if you substitute b, it is b, in place of 0 it is simply 0. So this integration is resulting the value of b. That means this is equal to E naught square by 8 d integral 0 to a b dx. Okay, so this is b. So if you bring this b also to this side, you are going to get E naught square by 8 d b integral dx, that is x over the range 0 to a, and if you substitute a minus 0, that is a, and so the energy stored is equal to E naught square by 8 a b d. So ABD is the volume. So E naught square by 8 ABD. So if we see that Q we have already defined this Q as equal to omega W by P, or we have defined this Q is also equal to omega mu into volume by Rs into surface area. Rs into surface area. So now let us find in the similar way we find the surface area, that is power loss over the surface area. So but here we have to consider the different planes like xy plane, yz plane and xz plane, and has to find the surface area. So we are going to get Q so anyhow we write Q here. This Q is equal to W omega mu volume by Rs into surface area. So